So let's get on with it. It's raining outside, we're in a pandemic, let's do some chemistry. There's the grade boundaries here for the 50-point test. Okay, question 1. Estimate the initial temperature. Well, the initial temperature was when you had 0 volume of acid added. So let me extrapolate back to that time. To that 0 volume added. All right then, so that gives me about 21.3 degrees centigrade as my initial temperature. Now, only 40% of people got that correct. Well, and that messes up the numbers for the rest of the question. But you might get error carried forward. Okay, 90% got the next one correct, which is what's the maximum temperature? So, of course, you're supposed to extrapolate it like this, from this decreasing temperature line, find out where they cross here, and then that is going to help you work out the maximum temperature. But you could just read it off the graph. The extrapolation was so small, the angle was so shallow of this graph, that the IB messed it up a bit there. Not to worry about that, things happen. So let me tell you that it comes out at about 29 degrees centigrade is the final temperature. Oh, hear that rain outside. So 29 degrees centigrade. Sticking with 1 decimal place like before. Okay, the concentration of ethanoic acid. So concentration is moles over volume. So somehow we've got to come out with moles over volume. Well, I know the volume. The volume of acid added corresponds to the volume here, which is 26 millilitres. That is when the temperature was at the maximum. So as hot as it got, that was when the reaction finished. After that, you're just adding room temperature acid, the temperature goes down. So maximum temperature means your reaction's finished at 26 millilitres. So now I need to work out the moles of acid. And how am I going to do that? Well, a little bit of stoichiometry. Sodium hydroxide plus the ethanoic acid goes to sodium ethanoate and water. So there's a 1-to-1 ratio between the sodium hydroxide and the ethanoic acid. So I can work out the moles of sodium hydroxide, and once I've done that, that's going to be the same as the moles of ethanoic acid. It's a 1-to-1 ratio. So moles is concentration times volume. I have the concentration and the volume up here. So that's going to be 0.995 multiplied by 50. Don't forget to divide by 1,000. Okay, let's do that calculation. Uh, 0.995 multiplied by 50 divided by 1,000. Okay, so that's my answer there. So I've got this many moles of sodium hydroxide. I also have that many moles of ethanoic acid, 1-to-1 ratio. So concentration is moles over volume. I've got 0.04975, and the volume I worked out above here of the acid, 26. So divided by 26 over 1,000. Let's work that out. So I've just got to divide this by 0.026, which gives me 1.91. So it's 1.91 moles per decimeters cubed. They didn't want the units in this case because they'd asked for it in moles per decimeters cubed, I assume. Yeah. Okay, D. Determine the energy change. So in the data booklet, if you can't remember, the energy change is Q is mc delta T. So I've got Q equals mc delta T. M is the mass of what's been heated. Well, I've got 50 millilitres of the sodium hydroxide from the question and 26 millilitres of my ethanoic acid. Now hold on, I need mass, and that's millilitres. Well, 1 millilitre is 1 gram. So I can change that to grams. And since the question wants it in kilojoules, I better be in kilograms. Kilojoules gives me kilograms. So I have to divide grams by 1,000. None of this has got you your first point, by the way. Then multiply it by C, the specific heat capacity, 4.18 kilojoules per kilogram per degree C. And then multiply that by the temperature change, delta T. So what's my temperature change? 21.3, start to 29, that's 7.7. So 7.7 degrees C. Let's work that out. So 50 plus 26, divide by 1,000 to get it into kilograms, multiplied by 4.18, multiplied by 7.7. Okay, 2.44. Now I've got one sig fig here, two significant figures on 7.7, 2.4 kilojoules. Next question. Only 25% got this correct. Now, if you couldn't do the one above, just make up a number, 10, lose the points, and try this one, if you know how to do the delta H. So delta H is going to be Q over moles of the chemical that was heating stuff up. It's not in the data book, you have to learn it. So Q, well, I've got that's 2.44 from the question above, and that's kilojoules. And how many moles? Well, I've got this many moles of the sodium hydroxide, and I've also got that many moles of the ethanoic acid. Do you add them together? No. Just pick one. Just pick one of them. So it doesn't matter. They're the same, but don't add them up. 0.04975. So that gives me 49. I think it was that. 49 kilojoules per mole. And I'm back to my 2 sig figs because of this 7.7. Do they care about sig figs today? If they do, they don't mention it in the mark scheme. Okay, next question. EI, terrible. That's what they said in the examiner's report, terrible. Okay, you're mixing a metal carbonate, let's say chalk with vinegar. Chalk with vinegar under 2 separate conditions. Explain the shape of curve X. So the gradient of curve X is decreasing. I can see that because it's steep at the beginning and then it's flat at the end. So the gradient is decreasing. It's decreasing. And why is that? Well, the rate of reaction is proportional to the gradient of this curve. The quicker the gas comes out, the faster the rate of reaction. So if the gradient's decreasing, the rate of reaction is decreasing too as time progresses. So that's one point. But why? Well, it's to do with collision theory. Collision theory is for a reaction to occur, the reactants must collide in the correct geometry with energy greater than activation energy. So which of these three, or all three, apply here? Well, to be honest, it's just the first one. The reactants are colliding. At the beginning, there's more reactants per unit volume, so there's more collisions per unit time. There's just higher concentration. Now, it's nothing to do with the collision geometry. That's never the answer. And it's nothing to do with the energy. The third part of collision theory is nothing to do with the energy, because energy is to do with heating it up and cooling it down. So the reason it gets slower is there's less collisions per unit time. Less collisions per unit time as the reaction proceeds. Let's see if that's right. Okay. Slope decreases, volume produced, frequency of collisions, rate depends on frequency of collisions. Nice. So that's my 2 points there. EII, X versus Y. So whatever happened in reaction X, Prague, it's normally this exciting. So X, there's twice as much gas produced, so there must be twice as much of the limiting reactant. So if the limiting reactant's chalk, you've got twice as much chalk, metal carbonate. If the limiting reactant is the vinegar, you've got twice the concentration of vinegar, because it says the volume's the same. So X, there's more of the limiting reagent, about twice as much. What's the model answer? There's more metal carbonate or higher concentration of ethanoic acid. Yes, actually my answer's better. But there we go. Question 2. Explain the general trend across period 3, first ionisation energy. So the first ionisation energy is the energy it takes to pull an electron off of a gaseous atom. So the higher the energy, the harder it is to pull the electron off. So as we go across period 3, well, each of the atoms has 3 shells, but they get smaller and smaller as you're adding more and more protons to the nucleus. So why is it easier to pull it off of this one, sodium, and harder to pull it off of that one, argon? Well, if you were moving an electron, you were moving a negative electron from a positive nucleus. So for sodium, the electron is further from the pull of the nucleus, and for argon, the electron you're looking at is closer to the pull of the nucleus. So there's more electrostatic attraction. So how are we going to get 2 points there? Explain for the general increasing trend. So the valence electron is closer to the pull of the nucleus in argon. Closer to the pull of the nucleus. Normally you have to say the pull of the nucleus. As the period is crossed. I bet that's 1 point. And then you have to say probably increasing electrostatic attraction. I bet that's for the second point. Okay. Atomic radius decreases. Greater energy needed to overcome the attraction. Yeah, that's it. So those are 2 points there. The next one, 25%. This is one of the trickier things to teach as a teacher. Why is it that lithium has a higher melting point than cesium? Well, lithium has small ions, and cesium has big ions. Now, they're both +1 charge. So cesium has the lower melting point, so it must have weaker metallic bonds. So if it's for 2 points, I bet that's one of the points. It's weaker metallic bonds. Weaker metallic bonds. Now, why does cesium have weaker metallic bonds? Well, cesium ions have a lower charge density. So it has a lower charge density. In cesium. So let's think about that. Lithium's a tiny ion with a +1 charge. Cesium's a big ion with a +1 charge. What's more attractive? Well, the lithium ion's more attractive because that +1 charge is concentrated on a small surface area. Or you could argue volume, either is acceptable. Cesium's less attractive because that +1 ion is spread out over this enormous surface area. So it doesn't have much electrostatic attraction. Is that right? 2b, smaller charge density, force of attraction between the ion and delocalized electrons decrease. Yeah, I think we got there. Next one. 2C, phosphorus 5 oxide. Now, non-metal oxides make acids, like sulfur oxides make sulfuric acid, nitric oxides make nitric acid, carbon oxides make carbonic acid. So phosphorus oxide, I bet that makes phosphoric acid, H3PO4. H3PO4. So now we've got to balance it. Okay, let's look at the phosphorus first. I've got 1 phosphorus and 4 phosphorus. So let me put a 4 here. That's fixed to phosphorus. Now I've got 12 hydrogens here. So if I put a big 6 there by the water, I've got 12 hydrogens. And now I've got 18 oxygens 16 oxygens on both sides. Nice. So that's right. 2C. Just 1 point. 2D. Describe the emission spectrum of hydrogen. So don't be banging on about electrons jumping up and down and bigger jumps of bigger energy and concentric and converging shells. No, no, no. The emission spectrum of hydrogen is really simple to describe. It is lines that converge at high energy. Lines that converge at high energy. No more, no less. Well, let's check. Series of lines converge at high energy. Smashing. That was quick. 2E. Strongest reducing agent. Well, first of all, let's think. If manganese is the most reactive, manganese is a metal. So metals hate electrons. So that means manganese wants to lose electrons the most. It hates electrons the most, if you will. And silver, well, that's the opposite. That wants to hold on to its electrons compared to the others. So a reducing agent. A reducing agent is itself oxidized. And oxidation is loss of electrons. So the question's asking, which of these loses the electrons the easiest? Well, that's going to be manganese. It's the most reactive metal. Metals want to lose electrons. If you were guessing, you'd have to choose manganese or silver, top or bottom, wouldn't you? Not nickel. So, voltaic cell made up of manganese and nickel. Okay, so I know that manganese hates electrons more than nickel. So manganese is going to turn to manganese 2+. Okay. Now you just have to put the other one in and make sure it's balanced. Nickel 2+ plus nickel. That's it. You've got to make sure the most reactive metal loses electrons. Is that right? Yeah. 2EIII, a voltaic cell. Now don't get that confused with electrolytic cell. This is making voltage. Let me just draw in the voltmeter. Don't put in a battery. And the salt bridge as well. Is that enough? Draw and label the connections needed to show the direction of electron movement. Label the connections needed. So the connections needed, I don't know if that's a wire. Is that what they want? That's the salt bridge. Now the most reactive metal's giving off electrons. So the manganese is the most reactive. So the electrons are going to go this way. The passage of the electrons is going to go that way. Is that enough? And the flow between the two half cells of the ions. Oh, I have to think about this. All right then. So as manganese turns to manganese 2+ and 2 electrons. So what's happening is this cell here is becoming more and more positive. The manganese 2+s are building up and building up. So what's going to be attracted to the manganese 2+ is going to be the negative ion in the salt bridge. Because negative ions are going to go over, attracted to the 2+. So whatever the negative ion in the salt bridge is, it's going to go towards the manganese, and the positive ion in the salt bridge is going to go towards the nickel. Just the opposite. Is that right? Cations to the left. Plus E-cat. Cations are plus to the left. That's it. All right. Oh, that was tricky. 45% of people got that right, or they got 45% of the marks. Question 3. Lewis structures. I urge you to look up how Lewis died. Interesting guy, but apparently a bit of a grumpy geezer. Okay, PF3 and PF, Vesper, molecular geometry. Alrighty, so phosphorus and fluorine. Going up to the periodic table. Phosphorus is in group 15, so it has 5 valence electrons, and fluorine is in group 17, so it has 7 valence electrons. All right. So adding up the valence electrons, 5 plus 7 plus 7 plus 7. I want pairs. It's valence show electron pair repulsion. So what's that? 20. That's 13. So I've got 13 valence electrons pairs to play with. So P goes in the middle because it's the most electropositive. well, actually, because it's the first one in the formula, and surround that P evenly by the other elements. Now let's draw the lines in. I've got 13 lines to go. 1, 2, 3. First of all, join them up. It's never going to be a ring, not in SL, and only rarely in HL. So never a ring. Right, I've got 13 lines to distribute, and I've put in 3. I've got 10 more. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you're looking for stable octets. There should be 8 electrons around the phosphorus and the fluorine. Of course, that means 4 lines, because each line is a pair of electrons. And for the next one, PF4+, I've got 5 plus 7 plus 7 plus 7 plus 7. Take away 1, because I've lost an electron. Divide that by 2, 28, 23, it's 22. That's going to be 11 lines. Is that right? 28. No, that's wrong. 28 minus. That's 32. That's 16 lines. 16 lines. P in the middle. And then surround it by phosphorus. Phosphori? No, fluorine, you idiot. Surround it by fluorines. And I've got those 3. Now I need... Oh, it's just 3 more on each one, isn't it? Okay. Now if you did that, you get it wrong. You have to put the square brackets in, and you have to put that plus, or the IB won't give you the point. Okay. Molecular geometry. So for 3A, this is a phosphorus trifluoride. You can see that the central atom has 4 electron domains and 1 lone pair, which makes this a trigonal base pyramid. For the next one, PF4+, the central phosphorus has, again, 4 electron domains around the central atom, but no lone pairs, so this makes this a tetrahedron. For 3B, they want to know if this molecule is polar or non-polar. So if this is fluorines, fluorine is the most electronegative atom on the periodic table. So that's going to drag the electrons in the bonds down towards the bottom. So the bottom's going to be a little bit negative, top's going to be a little bit positive. So this is going to be a polar molecule. Well, that's very wordy. So for 1 point, here's the answer. Any molecule that's polar is polar because the bond dipoles don't cancel. So here the bond dipoles don't cancel. Okay, I think this gets my vote for one of the hardest ever SL questions. It took me way longer than 4.5 minutes to work it out and to do it. Part of the trick is you have to keep as many decimal places or significant figures as you possibly can. Otherwise, you'll end up with an answer that's going to be slightly wrong. So here's how you do it. If I know how much carbon is in the carbon dioxide, then that's also the mass of carbon in the menthol, not methanol. There's a lot of people made that mistake, menthol. If I then work out how much hydrogen is in the water, that's the same as the hydrogen in the menthol. And once I know the mass of carbon and hydrogen in the menthol, any remaining mass must be the oxygen. So how do you work out the mass of carbon in carbon dioxide? Well, it's going to be 12/44. How do I get 12/44? Well, the molar mass of carbon's 12, the molar mass of a carbon dioxide is 44, so 12/44 of the mass. So this is going to be the mass of carbon. One, two, 0.1225 grams of carbon. And by the same logic, we've got 2/18 of the mass of water is going to be hydrogen. Why isn't it 1/18? Well, it's H2O, isn't it? Don't forget there's 2 hydrogens in water. So 2/18 multiplied by... So 0.0204. grams of hydrogen. So any remaining mass must be due to the oxygen. I've accounted for the carbon and the hydrogen. So what's the mass of oxygen? It's going to be 0.1595 grams for the menthol, minus the mass of the carbon, minus the mass of the water, of the hydrogen. So that's going to be the mass of the oxygen. So that's going to be 0.0166 grams. That's my mass of oxygen. And we're only about halfway there. Now we have to work out the empirical formula. That's pretty straightforward. So you write out the atoms big. I want their molar masses at the bottom, 16, 1 and 12. And put the masses at the top. So I've got 0.0166, 0.0204, 0.1225. So do the calculation to work out the number of moles. Alright, so now I need to get integers out of this. So the best way to do that is to divide by the smallest number, which in this case is the number for oxygen. So divide everything by the smallest number. Which gives me, well, that's 1 oxygen. And that's going to be 9.8 carbons. And hydrogen, oh man, that 9.8 doesn't look good, does it? Hydrogen is 1.0204. Okay, 19.6. Now normally, if you've got a 0.8 or a 0.6, you wouldn't do what I'm going to do now, which is just round. C10H20O1. So how comes, which is the correct answer, so how comes it's not exact? I'm sure the data will give me exact numbers because I didn't use the correct molar masses. I used 12 instead of 12.01. So that's a ridiculous question. I'd love to know how many people got that right. I would imagine 0.1%. Oh, just because you had trouble thought me, no one can do it? No. Trust me. Okay, question 4b. I've got to work out the molar mass of a gas. So that has to be PV equals nRT. And where's the molar mass hidden in that? Well, remember you did the lighter experiment where you collected the bubbles and worked out the molar mass of the gas. N is moles. Well, actually, also moles is mass over molar mass. So there's molar mass that's hidden there. So hopefully the IB have given us the 5 variables and we can calculate the molar mass. So molar mass is going to be mass times the gas constant times temperature divided by pressure volume. What's the mass? 0.150 grams, 3 sig figs. The gas constant, in case you've forgotten, here it is, the gas constant, 8.31. 8.31, and the temperature has to be in Kelvin, but they've given it to us in degrees C. Interesting. It's -1 decimal place there, 273. Pressure has to be in kilopascals, which it is given in kilopascals. And the volume has to be given in decimeters cubed. It's given in decimeters cubed. All right, let's just calculate the answer and hope it isn't something crazy, like a negative number or less than 1 or like a million. It's molar mass after all. So 0.15 times 8.31 times that divided by okay, 156 grams per mole. I'd argue that this here probably sets us to 2 sig figs, I'd argue. But the IB has given it to 3 sig figs, so that's okay. I don't think they're going to worry about that. Equilibrium. Many reactions, state of equilibrium. Okay, so Le Chatelier's principle states that for a system in equilibrium, if it's stressed, it will move to oppose the stress. All right then. So if I increase the volume, that means I'm going to decrease the pressure. If you make the volume bigger, the pressure inside is going to be smaller. And if I've stressed it by decreasing the pressure, the reaction is going to want to increase the pressure. How's it going to increase the pressure? By moving to the side with the most gas particles. Now, there are 2 gas particles on this side, and there are 2 gas particles on that side. So increasing the volume has no effect. See, the effect on the position is no effect. And the reason is there's the same number of gas particles on each side. Same number of gas particles on each side. Okay, if I increase the temperature, I stress the equilibrium, and it wants to move to decrease the temperature, move to the endothermic side. So we have to decide which side is the endothermic side. So this is delta H negative, so that's the hot side. That's supposed to be the devil, that's the hot side there. And then the other side is the endothermic side, and that's supposed to be a snowman. So it's going to shift to the endothermic side. So it's going to shift to the left, and the reason it's going to favour the endothermic side. Right, is that right? No effect, moves left, same number of gas particles, full reaction is exothermic. Nice. Okay, 5b. These equations identify the 2 different amphiprotic species. Okay, so amphiprotic means that it can give away a proton or it can receive a proton. So we have to look at those equations and see which chemicals, which species, give away protons and receive protons. All right then. So looking at this first one here, it's accepted a proton to turn into that, and it can give away a proton to turn into that. So definitely HCO3 minus, that's amphiprotic. Let's look at the water. If water has lost, the water here, water has lost a proton, yep, to make OH minus, and here it's gained a proton. Okay, so it's those first 2 chemicals, HCO3 minus and H2O. Are both amphiprotic. Yeah. 2, the conjugate base of the hydroxide ion. So the conjugate base of the hydroxide ion. I remember a conjugate acid is made by adding a proton. So a conjugate base, I have to take off a proton. All right, so let me take off a proton, an H+. That's going to give me the rather weird O2 minus. Yeah, so I did 2 questions in one there. So conjugate base, remove a proton, and the next one is it makes O2 minus. So conjugate base of remove a proton from an acid. Nice. Next up, C. a student working in the laboratory classified nitric acid as acids based on their pH. All acids contain oxygen and hydrogen. Evaluate this hypothesis. Well, no, that's wrong. The hypothesis is wrong because I can think of some acids that don't contain oxygen. For example, hydrochloric acid, hydrobromic acid, hydroiodic acid, or hydroastatinic acid. So that part's wrong. But all acids contain hydrogen. Well, all Bronsted-Lowry acids contain hydrogen because they give away an H+. So I think it's correct to say that all Bronsted-Lowry acids contain hydrogen. If you're high level, there's such a thing as Lewis acids, which is all blah, blah, don't worry about that. We're doing the SL paper. Am I right? So we got 1 point for saying that these acids don't have oxygen, so a point for that. And then we've got another point for saying he didn't test enough acids. Okay, I like my idea that all Bronsted-Lowry acids contain, but not the Lewis acids. Now the Lewis acids is in the mark scheme, but that's high level stuff. It's kind of confusing. So we'll go for the second point is he didn't do enough samples because he only had limited samples. Alrighty, moving on to question 6. What chemistry can I use to distinguish between these two very close isomers? Well, this is a secondary alcohol and this is a tertiary alcohol, and they have different chemistries. How do I know it's secondary? Find the OH, find the carbon attached to the OH. How many carbons directly attached to that? 2. It's secondary. For tertiary, find the OH. Find the carbon attached to that OH. How many carbons directly attached? 3 of them. So it's tertiary. You can oxidize primary and secondary alcohols, but you can't oxidize tertiary alcohols with acidified dichromate. So deduce the type of chemical reaction and the reagents. So the chemical reaction is oxidation, and the reagent is acidified dichromate solution. If they want to know any more than that, colour changes and whatnot, let's have a look. State the observation expected. Okay, so for A, I'm going to turn my secondary alcohol into a ketone, and so the colour of the dichromate is going to go from orange to green. And the reason why is because we've gone from chromium 6+ to chromium 3+. And you can't oxidize a tertiary alcohol like this, so there'd be no change. So apparently there was no points for saying the oxidation states, but you did have to mention that this was a secondary and that was a tertiary. But we got those points from up above, so I think we're all right. 6AIII, H1NMR. Okay, that's some busy compounds we're looking at there. So H1NMR looks at the hydrogen environments and the ratio of the hydrogens in those environments. Oh man, so let's count them up. So these are the same, so that's a peak of 6. Area 6. This is different. This is different. And this is different to everything else. And that's different. So I think for the first one, 61111. Okay. So signals 61111. I think there's 5 signals. Looking down at B, for B, just fill these in. These are the same, so that's 2. These are the same, that's going to be a 6. This is different, and that's different. So I think that's going to have 4 signals, 2611. So 4 signals of 2611. Wow, that's one of the trickiest ones they've ever asked. 2611. Let's see if I'm right. 56111. Yeah. Nice. I kind of like H1 NMR. 6B, free radical substitution. Oh man, now a lot of people come out, I've had people come out of exams saying we never did this. We absolutely did this. It's initiation, propagation, termination. The mechanism of free radical substitution. So 4 points. So I suppose we better have an initiation, a propagation and a termination. Okay, so initiation. That's BR2 goes to BR dot plus BR dot. And that's with ultraviolet light. That's 1 point, I'm sure. Then, and the rule is you can never make an H dot. So whatever you do is okay pretty much, as long as you just never make an H dot. So I've got my ethane. And, well, what else am I going to do with the ethane? It has to be with a BR dot, isn't it? There's nothing else going on. And so I can't make an H dot, but what I can do is I can make HBr, and then I can make this C2H5 dot. There we go. So that's a propagation step. Dot goes in, dot comes out. Let's do a couple of termination steps. Why don't I do a C2H5 twice, and that goes to C4H10. And maybe one more. Hell, let's do the easiest termination step. That and that makes that again. So termination step, 2 radicals come together, 2 dots come together, disappear. No more dots. Alrighty. So 1 point for that. 1 point for that. Haha, they allowed my cheeky one. Oh, that was really stupid of me to put a dot here to end the sentence. No. I shouldn't have put that dot there. I'm going to give myself a tick. But this one here, you know what? The IB wanted 2 propagation steps and not 2 termination steps. So I lost a point. That just doesn't seem fair because they weren't specific about that. You had to label each step: initiation, propagation, termination. So let me take out this termination step because they only wanted 1 termination step. And let me put in another propagation step. Okay, so let's have C2H5 dot plus BR2 goes to C2H5 BR plus BR minus, BR dot. See if they like that one. Yeah, that's the second one they've got there. Nice. So I would have lost a point for that, but I don't think that was fair. Wow. I can't tell you how much work these paper 2 ones take to try and get everything just right. This is killing me. I'm not sure I'm going to do many more of these. This took me the better part of a day. Anyway.